Andrew.
I didn't raise my hand.
All right. So I cut Melissa off, I guess.
The only reason I'm asking is, how would you give an example where the light would change?
How would I give an
I
example?
know
of what?
that, for example, light is constant all the time, right?
Right.
So when would you consider it when it's changing?
When light does die down and disappear?
Yeah, exactly, yeah. And when
What happens there? All right.
Yeah.
So what's happening there is that all matter is made out of charges.
Okay.
And when light interacts with charged particles, because it's electric field and magnetic field, it actually accelerates them, which ends up using up some of its energy.
And that's when
And then it dies down. It becomes heat after that.
And that's
So-
when you turned out the acceleration, and we're not
No.
trying to
It's not even that. It's not so much accelerations. We just steal the energy and the magnet. It still goes at the speed of light, but its amplitude dies
Can
down.
you give me an example of when it continues to infinity and when it does and when it dies down?
It never slows down, never speeds up, but if it interacts with material, its amplitude can decay down to where it stops existing. And this is as simple as go out on a day that's warm and sit with your back to the sun, and after a while your back is warm. That's
And
because
then
you
the
have
light
absorbed the
burns
energy of the
out
light
and
into your
heat.
skin.
And
So,
then when it continues, because you said light can go into infinity,
yeah, so if I'm in empty space
Okay.
and I shine the light, it'll go forever.
as long
'Cause
as
there's nothing to interact with.
unexpected, okay.
Yeah, so
That makes
it has to
sense.
interact with charged particles
Okay.
to end up using its energy up to change the kinetic energy of some charged particle.
Thanks.
All right? Yeah. So at this point then, what we've done mostly, yes?
So then light radiates at all just because of entropy, the same reason heat radiates or anything else? Is that?
I'm not sure if I completely understand your question. Are you asking why does light get emitted? Why does it radiate?
Yeah.
All right. So actually it's a little just a bit more complicated than that. What happens is what causes light, the ultimately source of all light is electrons jumping. All right? So what happens is that because atoms have discrete energy levels, and we will study this more later, but because atoms have discrete energy levels, in chemistry you've probably heard about the different shells of energy. Mary, I really hope that's physics. Okay, so the electrons jump between allowed energy levels, and the problem is that they do it in clumps. All right, so what I mean by that is we don't gradually drift in, they go from one energy level to the other. And because energy has to be conserved, the only way to conserve energy is to emit the amount of energy that the electron loses as it jumps, and that comes out as light. That's ultimately the source of all life, of all life, also life, but that's not what I meant to say. If I get the atoms pressed together close enough, the energy levels available become very closely spaced, and with that in mind, then we can get a full continuous spectrum of light that comes out. So basically it's because electrons that go around the nucleus act like little antennas, broadcasting antennas, and they send out light waves. All right, that's another way to look at it. And so ultimately it's tied to electrons, it's tied to the charges inside the atom moving, which is what produces the light. Okay. All right, so we've talked about velocity, we've talked about time dilation. We did talk a bit about length contraction, but I want to be sure you're clear on that. Do you understand what causes length contraction? I know causes, because I really don't know the cause of any of them. Do you understand how to solve problems that involve length contraction? If I tell you I have a meter stick that appears 60 centimeters long, could you tell me how fast it was moving? I mean, not off the top of your head, but could you figure it out? All right, so let's do this then. I tell you I have a meter stick and it looks 60 centimeters long. All right, so I have 60 centimeters and I have 100 centimeters. This is the meter stick, this is what it looks like. Which of those is proper length? How do you know that? Just the definition. How long does it look if it's sitting still with respect to you? So this is my L naught. This is my L. What ties L and L naught together?
Gamma.
Gamma. All right, so I say that L equals L naught. How do I fix this equation? How do I know that we're going to put it over gamma instead of multiply by gamma? Because it's called
More proper.
length contraction. And that's how, if I have T and T naught, how do I know that I multiply by gamma?
Dilation.
because it's time dilation. So I need to make time bigger, I need to make length smaller, shorter. And gamma is always larger than 1. So when you multiply by it, you get a bigger number. When you divide by it, you get a smaller number. All right, so this is how we do with length contraction. Yes? Oh, that's not a question. That's just a hand at eye level, which gets called on. All right? All right, so if I give you a bunch of lengths, and I'll say those are all meters. All right, so that's 1, 1.2, 3, and 0.9. They're all meters. And I tell you one of those is proper length. Which one is it?
3.
1. If it's 1 meter, it's
Repeat the question.
I say this is the same object under various conditions, and one of those is the proper length. 3. Does everybody see it?
Yes.
With lengths, the largest one is, if you know one of them is the proper, because everything else is length contracted, so all the smaller numbers are not the proper length. If I just now flipped it and said, okay, no, those are actually seconds. Now which one's the proper time if one of those is guaranteed to be the proper time? 0.9. Because with time, the smallest one, if you know that one of them is the proper time, the smallest one is the proper time. With length, the largest one is the proper length. Yes?
Good question. Does that happen just on x-axis, y-axis?
So it only acts in the direction of motion. It's a very good question. So if I were to take a box of chalk and go like this, the only place length contraction would occur is here. This would stay the same height. So it only contracts in the direction of
So if you
motion.
have like, if you're traveling in a station and you have like a kind of cord or something, and it goes 5 feet, is it still 5 feet?
Yes.
No matter where it goes?
For any observer, it would still be 5 feet
Oh, okay.
because it's vertical to the motion.
What if that box goes in diagonal fashion?
No, I mean, so that's a fair question. So what happens is if I go diagonal, the part of it that's perpendicular is the part that shrinks, nothing else does. The dimensions, all the dimensions perpendicular to the motion all shrink by the same factor. It can make it a very strange looking shape. In fact, and I don't know, this just in my head is filed material, you don't need to worry about it, but for some weird reason, if you have a sphere that moves near the speed of light, forget how this all works, but it still looks like a sphere. The way it shrinks, it's bizarre. I don't remember all, there's some other things that factor in. I'm not going to go there. Just remember, you can look it up. It's a weird fact.
I'm just confused. Like, okay, so if age changes this way, how does this?
One's time dilation and one's lengths.
Okay.
So they're very different things.
Oh.
So one's actually the geometrical shape of it, and one's actually how old is something getting.
Formula one. How does that
I mean,
change?
Oh, because this is your age and this is your length.
Oh, so gamma.
Gamma is the same factor, but gamma is being multiplied when we're looking at times. It's being divided when we look at lengths. All right. So we're I'm ready to move on past this now a little bit in that we've got a couple other things that we want to talk about. Well, or just a couple. The famous equation that everybody knows is E equals mc squared. Lots of people have argued about this, and what I need to tell you right up front is to interpret this equation, you have to make some definitions. And some people define it one way, other people define it another way, so they get different answers and then they argue about it. It's one of the most stupid arguments in the world. It puzzles me that PhD people will actually do this because you can look at it and go, it's just a matter of the definition. It's like, it's as silly as this. If I define overweight as anything over 30 pounds, you may think it's a stupid definition, but you will at least know where I am, and we can make calculations based on my definition. Do you understand what I'm saying? Once a definition is given, if you accept the definition, certain things follow. You may not like the definition, and that's perfectly fair, but what you say is, once that definition is given, I'll get the same answers you get with that definition. So the problem we have in this is this the mass at rest, or is this the mass that it appears to have when it's moving? All right? And that's one of the biggest things that people argue over. I'm not even going to countenance that argument. I like to refer to them as rest mass or proper mass and relativistic mass to keep them separate, but I'm going to go ahead with how your author does things. So, I mean, it's not even a thing that needs to be argued about. But what does need to be discussed in this equation, all right, is does this equation imply that matter can be converted into energy? Don't fall asleep on me, Arturo. It just makes me jealous. So, you've all heard that matter can be converted into energy and energy can be converted into matter, blah, blah, blah. You tell me you've all heard that somewhere before.
No.
Oh, good. Don't listen to it now then. It's a lie. People say, well, if this says E equals mc squared, that means I can convert matter into energy. And in chemistry class, they'll usually say, when you have an atom assembled and it's, you have the binding energy, that then some of the mass is converted into energy, blah, blah, blah. And that's not what this equation says. It's just as simple. I can prove this to anybody who's had one algebra class ever. What does conversion mean? Here's a conversion equation. This is called energy conservation. It says if K plus U is the total energy, then delta K plus delta U will be 0. This is a conversion. Why is it conversion? Because in order to keep this 0 is if you have one, I guess it's easier to think of it this way. Here's my 0 energy, and I've got my pen up here. What kind of energy does it have? Potential. Everybody see that? As I drop it, does it lose potential?
Yes.
Does it gain kinetic?
Yes.
Yes. So as I lose one, I gain the other. Does that make sense? All right? So that's conversion. What we have here is, what if I cut the mass in half? What happens to the energy? I cut it in half. It's not conversion. It's parallel changes. In other words, this says, if you lose kinetic, you lose potential. That's what this says. If I lose one side, I have to lose the other side because it's an equation. If I cut one side in half, I have to cut the other one in half. It's a stupid, stupid thing to say that this implies that mass can be converted into energy. It was even so far that textbooks like Surway, who is a really famous textbook author, would say, calculate the energy you would get if you converted a grain of sand into energy. And he wanted you to take the mass of a grain of sand, multiply by c squared, and find the energy. It can't be done by any process known to human beings. It's a stupid question. You can't do it unless you watch enough Star Trek or something.
Maybe the conversion they mean to say production of energy.
But it isn't a production of energy. See, here's the thing. They tell you that during a nuclear explosion, that what happens is that some of the mass is converted into energy, and that's where the energy from the nuclear explosion comes. This equation does not predict that. So here's the problem. If you take a uranium atom, and guys, this is very conceptual, but it's in you should be able to understand it, so work with me. I have a big globby uranium atom. They're huge, right? They're actually somewhat unstable. So what happens, if it absorbs a neutron, it makes it kind of jiggly and wobbly, and it can break into 2 pieces. Now, uranium, where is it on that chart? Does anybody happen to know? What number is uranium? 92. All right? What does that 92 tell me? There are 92 protons. Are those protons friends? No, they're not friends. They detest each other. You understand, they're exerting forces to try to push each other away at all constant times. The only reason that they don't make it is the neutron's somewhat moderated. But if that atom splits apart into 2 pieces, the strong nuclear force is suddenly overcome, and you've got 2 very highly charged positive nuclei sitting next to each other. What do you think happens?
Repel.
They repel at enormous force, enormous speeds. So before it split, this was the total energy. After it splits, we've got the mc squared of the 2 pieces plus the enormous amount of kinetic energy involved that keeps the total energy constant, because energy is conserved. Are you with me? So we've got 2 pieces, but they're moving at really high speeds. But I want to find out what they are. In order to actually sit and weigh them, I need to stop them, don't I? So to stop them, am I removing energy from the system? They're speeding away. When I stop them, I simply remove the kinetic energy from the system and have them sit still. When I take kinetic energy out of the system, what happens to the mass? Am I decreasing this number when I stop them? They have this energy, they're moving, now I stop them, they're no longer moving. So the total energy is now less. So since C can't change, what happened to mass?
Should change.
It also got Less. There was no conversion, it's parallel change. And now when I look at the two pieces, they have less mass than they started with, but that's because I went and stopped them. And people don't describe this correctly. I took energy out of the system, that's why they have less mass. They had the same mass before I stopped them.
Now to stop them, imagine they're high velocity kinetic energy, right? Now,
You have to put it through some thing like water or something that tends to absorb the kinds of energies that are associated, and some kind of a moderator that you just slow them down. All right, so what I'm trying to get you to understand is this equation is so often misinterpreted it drives me crazy. This equation merely tells you that E equals mc squared. If you got more energy, you got more mass. If you got less energy, you got less mass. So if I take my soup and I heat it up, what happened to the mass of my soup? It increased. Not by any amount that most scales would ever detect, but strictly speaking, if I increase the energy of that stuff, I have increased the mass. It is not conversion, it is parallel change. Right? Yes?
How would you measure that?
Carefully. It's somewhat theoretical, but it matches all the experiments we can do. I mean, no, you're totally right. There's no practical way to measure the increase in mass that I get from simply boiling a pot of water.
But the energy does increase, so therefore there is bigger.
Yeah, and we can basically make estimates about how much mass increase, but it's going to be way less than any scale can measure. But we do have experiments where we can measure it.
How so?
Because of the binding energies of atoms. And I've got to wrap this up because it's time for lab, but we're going to actually continue this discussion in lab, so we can.
does it mean that heating someone is making it heavier?
Heating something should make it heavier, yes.
Oh, really?
Strictly speaking, yes. But it turns out, but it's not going to be by very much. Right, so here's the thing. What then happens is, we realize that there's two ways to look at this, and if we decide that we want to actually analyze this from the point of view of mass being what we would call rest mass, then I can say what actually happens then is that the energy is actually equal to gamma mc squared, where gamma is my friend, and the mass in this equation is no longer the varying mass, but this is the mass something has if it's at rest. So this would sometimes be called the rest mass. So what we're saying by this is that gamma is a number always bigger than 1. So if I give it more energy, I can either say the mass increased, or I can say gamma increased. All right, and they're both equivalent ways of talking about the same thing. This is often done to make it very explicit that I've got it no longer at rest. If gamma's in there, I can see that this is not an mc squared because it's at rest.
One more question.
Sure.
Gamma in that situation would be the heat?
No, gamma is my good old friend 1 minus b squared over c squared. And it's going to be tied to heat because what is heat? What is temperature change? From last semester.
Movement.
You weren't there, so
I was there, but I don't remember.
you were here last
A
semester.
different.
Oh,
Changing kinetic energy.
it's changing kinetic energy. Kinetic energy is
Movement.
movement. So temperature is tied to how fast something moves.
So movement changes mass.
But not, in general, not, and see, it's just like everything else with relativity, not in your everyday life by any amount you can measure, but theoretically
But
it
it
does.
affects.
Right? So what happens is that if you heat something up, the mass actually increases, but you can also look at it as the fact that gamma is tied to V.
How does potential energy affect that equation?
How is potential energy?
Yeah.
There is no potential energy because all of special relativity assumes there are no forces, and without forces, there's no potential energy. Right?
That hurts my head.
I said it fast. So, where does potential energy come from? Give me an example of potential energy.
From something that is expected to happen but it doesn't happen?
Actually, I want something really concrete. No, I mean, so, like, does the chalk have potential energy?
Yes.
Where does that come from?
The gravity.
And yes, so gravity's a force, isn't it?
Yes.
Give me another example of potential energy. Somebody, anybody. What's another potential energy? We studied 2. What's another potential, we actually studied 3. What's another potential energy?
Springs.
Springs. And what do I have to do to get potential energy in a spring? I need to stretch it. And that causes a force in the spring, you've got a force again. Another potential energy is 2 positive charges next to each other wanting to fly away from each other. Is there a force?
Yes.
Yes. Anytime you've got potential energy, you've got forces. And so,
Force is a matter of
yes, and so when we started special relativity, what was the condition I said we needed to have right up front? No forces, no accelerations. All velocities are constant. that means that we are not ever going to have potential energies, therefore we're not going to consider that. Yeah. So with all of relativity, the basic idea that we've got going is that we're not going to have any accelerations, we're not going to have any forces, and therefore no potential energies, because without forces you can't have potential energies. Not all forces cause potential energy. So guys, in the lab, I'm just going to continue this topic, so I'm going to go ahead and finish it here before we go on down there, because this is what, there are no, you may just point to rockets, we have no rockets that will take you at point A, C, and so I'm just going to kind of hammer these ideas until hopefully some of them make sense. All right, so yeah, let's go ahead and head on down there, and then I'm going to work some of the next problems, but I also want to get some of these ideas. I really want the concepts in your head so that you're not the 90% of people who completely misunderstand the notion of relativity. That's right.
Because I completely forgot to answer one of the questions. The second word.
Did not understand. I don't think it's a small because and just because they got, however they got taught, it's not very like, some schools do this, some schools do that. But you do need to do this if you want to.
You can go to San Diego.
So but I recognize, and now you got
Do you visit?
Yeah, it's nice. It's just incomplete, right?
Well, like phones and check, right? That's confirmed if you want to take
What's
it.
that?
Nobody understands it. Everybody just does it, but nobody really understands what they're doing.
And I think
Wait, I think mine is
I find enough to know
No, it says both.
like even in
But then
the
also
textbook you read it and they make mistakes.
We were talking about you have the pin.
It's even like the whole thing. The problem we have with the way to explain it is that there's no way to explain fusion.
For that one,
Because if you're
Lost your scarf?
then fusion would never happen by that.
I was in the lab with you guys.
And sticks them together. And so by using their thing, you take their answer because you're not going to run it. And so it's just easier if you realize it's all tied to the idea that energy is changing.
Wait, show me on laptop, I can see. Yeah, the teacher.
Is that right? What'd you do? You alright?
Yeah.
Did you try down police services to see if they had it?
Not today, too busy to work on homework.
Okay.